Yeah, can everybody see that? Is that good?
Yes, we can see the screen now.
Okay, great. Thanks. So I'm Don Pierson and from Uppsala University, and I'm going to give a talk about the introduction to the ISIMIP lake sector. One thing I just say is that in my introduction there, I'm no longer the section chief of water quality monitoring in New York City DEP. That was something I did in the past. But now going on to the ISIMIP lake sector, basically what the ISIMIP lake sector is, or what, let's not talk about the ISIMIP lake sector right away. Let's talk about ISIMIP as a whole. And here I show the ISIMIP mission statement, and it says basically the ISIMIP aims to improve global and regional risk management by advancing knowledge of the risks of climate change through integrating climate impact across sectors and scales in a multi-model or impact framework. The point I want to make especially here is that it's looking at risks and it's looking at sectors. So basically what the ISIMIP project stands for is the Intersectoral Impact Model Intercomparison Project. So it's important, this intersectoral and impact models. So what the ISIMIPs, and of course it's involved with climate change. So what ISIMIP as a organization does is they have a number of scientists working on providing data that simplifies the process of simulating the impact of future climate change. And it does this by making a number of the GCM outputs that are sort of archived in something called the CMIP project, which is Coupled Model Intercomparison Project. And there was a number of these. These all are associated with the IPCC reports that come out every 5 years. And the ISIMIP 2 was working with the CMIP 5 data, and now ISIMIP 3 is working with the CMIP 6 data. And in addition to making these data available, it does something else. It makes the output of the different sectors that are involved in ISIMIP available to everyone in the world in a consistent archived format. So I'll go to the next slide. This just shows basically what I said, basically that the ISIMIP is putting climate input, and it goes into both global impact models and in some cases regional impact models. And then this can be used for assessment of the effects of climate change. So it's not, CMIP is concerned with simulating the atmospheric consequences of climate change. ISIMIP is interested in simulating the consequences of those changes on different things in the world, basically. And these are the sectors. And you can see there are many different sectors, but what we were involved with and have been involved in is the lake sector. And this is basically, we're using these data to simulate the effects of climate change on lakes. And we can do this both globally and also locally. So why would you want to be involved in using these data? And I would suggest, and when I said I no longer work for New York City Water Supply, but when I did, we did simulations of climate change impacts, and we spent a lot of time developing the data formats that you get directly from ISIMIP. And what that means is it's in a consistent format. The forcing data from multiple GCMs are available. And here's something important. They're on a common grid projection. It means that if you put your lake, give the longitude and latitude of your lake, and you get the grid associated with that, each GCM will have the same grid box. Whereas if you take it directly from the CMIP archive, that may not be the case. ISIMIP also produces a common bias correction. I'll talk a little bit about that later. But basically, it's the same bias correction applied to every GCM that's in the CMIP data set that ISIMIP works with. And you end up with a simulation hierarchy that allows you to look a lot at the uncertainty in climate change. So you can look at the effects of different GCMs, different emission scenarios, and different models. So it's a very good way to really get to understand what the uncertainty and what the sources of variability in your simulations are. And finally, because it develops this common archive of data, you end up with the ability to not only look at your simulations, but look at other simulations as well and compare your results, or even do connections with, say, the hydrology sector that might produce the inputs to your lake model. So there's many advantages to working with ISIMIP. This is just quickly to show you a few of them. I'll just talk about them a little bit more. First of all, like this is you can go into the CMIP data directly and CMIP6 archive, and this is the sort of part of the description of data. And you'll notice that the horizontal resolution of the grid varies between models. So this is what I was saying, that having it on a common grid avoids this problem. When we were working in New York, we had to regrid all the data because we wanted to get it all on the same grid. That's a lot of work. It took a lot of time. I had a postdoc spending lots of time doing that, and you don't need to do it. And then all the data are bias corrected. What bias correction means is that they look at, in this case, these global reanalysis data products, there's a number of them. And basically, they compare the historical simulations of the GCMs to the global data products, and they adjust them so they match. That's what reanalysis, or not reanalysis, but bias correction means. And this is done, again, consistently using the same method for all the GCMs that you work with. I think we're going to be able to send this presentation out to everyone. There's a lot of different links here that you can go to later and take a look in a little more detail. If you look at what kind of data we get from the ISIMIP climate scenarios that are available, this is basically the list of data for every grid cell for every day, and it's at a daily time step. So there's something like 18,000 grid cells that have lakes in them in the world, and it's a 0.5 degree global grid. And all these data are available at each grid cell for each GCM and for each scenario, future climate scenario, over the entire simulation period. So we'll go into that a little bit more. But the main point I wanted to make here is that these yellow things are basically what you need to run any lake model, certainly for the hydrothermal part of the lake models anyway. So everything you need is there. I mean, so it's really a great data set just to work with. And this just shows the scenarios a little bit. I'm going to talk about the two different scenarios, and I may mix things together a little bit because they're sort of pretty similar, but there's the ISIMIP 2 and the ISIMIP 3. And the biggest difference is that the ISIMIP 2 and the ISIMIP 3 use slightly different mixtures of GCMs, and the scenarios are a little bit different, but it's basically the same idea. I'll start with ISIMIP 2. And this is, these lines you could think of as global average temperature or some measure of climate change, but I think this is global average temperature. There's two main background sort of, you could say, scenarios. There's first of all something called the PI control, that's pre-industrial control simulation. And what that is basically running these GCMs, but running them with the pre-industrial carbon dioxide concentrations in the atmosphere. So it's giving you some variability, but it's variability due to other things in the model, not the forcing due to the increased carbon dioxide concentrations. Then we have a historical scenario, and the historical scenario is actually using the measured change in carbon dioxide over time, and that goes up to about 2005 or 2006 in these scenarios. And then after that, we have future climate scenarios where we assume different emission scenarios based on a whole bunch of socioeconomic modeling to get how people are going to change their habits and change their emissions and so on. So we have basically a RCP 8.5 in this case, which is basically business as usual, no significant changes, down to the RCP 2.6, which was the most hopeful scenario that we would stay under the 1.5 degree increase in global temperature. So you can then compare, like, what is the effect of climate change on my lake? Often you would take the historical scenario and compare simulation results with that with one of these future climate scenarios, where you force your model with either the historical data or the future climate scenario data. If you want to see the effects of climate change that already occurred, you can basically compare the PI control to the historical simulations. The one other thing, and now I'm moving to ISIMIP free, you'll see again, there's basically the same idea. And also I should mention that in addition to the climate data, there's also data, they've produced gridded data sets on changes in land use and some other socioeconomic things like population, gross domestic product, or some things on fertilizer use and dams construction. There's many, many different things, but there's supporting data that is not climate data as well. That's the main thing we should think about. And the other thing I wanted to point out is that in the ISIMIP free, there's one other type of simulation. It's called the counterfactual climate simulation. And what that is it's a historical scenario, but that has been adjusted to account or to remove the effect of climate change. And there's a whole methodology behind that. But the advantage of that scenario is that you can then use it to evaluate, say you had a really large storm and it has some big impact on your system. You could run the historical simulation and also the counterfactual simulation that removed the effects of climate change, and see how important climate change was in affecting that event. So this is a new thing that's available in ISIMIP free. And this is just, I want to just make it, this is just if you go into the ISIMIP website and look at the lake sector, you'll see that there's a controlled vocabulary and a format for uploading data. So everyone that does simulations then can upload their data to the ISIMIP data archive, and it'll have this, every file from every model will be in the same format. So it makes it very easy for you to, because everybody has to obey these rules, basically. And that means that it's a bit of a pain because you'd rather just dump your data up there. But I mean, in the end, it's really very good because everybody can then compare their data, their models to each other and look at the data. I'm almost over 10 minutes already, so I'm gonna, where did my slide go? So I'm just gonna quickly go through that. We're gonna have two, whoop, I went the wrong way. Where did my mouse go? I'm not gonna talk too much about this because we're gonna get two examples from Ruth and from Anna about the use of global and the local simulation capacity sort of in the ISIMIP project. The global is basically going with more or less uncalibrated models, but using the entire gridded lands data set, which is around 18,000 grid cells, where we have lakes where you can do simulations. And then there's the local models, which is basically allowing, are many Glion lakes where we have somewhere, I think around 70 lakes right now, where we have data not only for simulating, like, so we've downloaded the grid point, the grid cell for each lake. So we have the ISIMIP scenarios, but we also have the data for calibration. So we have bathymetry data for each lake, and we also have measured temperature data from each lake. So that's something we don't have for the global simulations. We do have bathymetry data, but we don't have data to actually calibrate against. So there's two different strategies here, and we'll talk more about this later in the presentation, so I won't say too much more. I'm going to try to finish off by saying there's two ways you can participate in ISIMIP. The first thing you can do is you can simply just use the ISIMIP forcing data to make future climate simulations. And then you can deposit those data into the ISIMIP archive. This is something we very much would like you to do. There's 18, as I said, around on the global scale, there's around 18,000 grid cells. This may sound like a big thing, and it often does require some special computing knowledge or skills, but we have people that can help with this if you want to try to do it. And then there's the local lakes, which everyone is familiar with, how to do those simulations, more or less. There's 70 free sites now available. And we also have 8 sites that you can do, 70 free sites for hydrothermal simulations, but there's also 8 sites now available for doing water quality simulations as well. And we still would like to build that up also. So that's another way you could participate. If you have a site that hasn't contributed data to the water quality part of this, please let me know, and we'll try to get your data included into the archive. And finally, in addition to making simulations, I just want to make a pitch for the fact that even if you don't want to make simulations, there's all this data there that can be used. There's presently 6 in the ISIMIP 2, CMIP 5 set of simulations. We've produced 12 terabytes of data on a global scale with 6 different hydrothermal models. Everything in ISIMIP 2 was hydrothermal models. And in CMIP 6, using the Lake Ensembler program, we've already, with 4 models, or with, no, I'm sorry, I'm jumping off. In the global scale, we've used 2 models already and produced 4 terabytes of data with the ISIMIP 3 or CMIP 6 forcing data. On the local scale, in ISIMIP 2, we used 8 models. On those 7, it's not quite 70 lakes in that case, it's a little bit less, but there's 50 plus lakes with 8 models of hydrothermal simulations, and there's around 500 gigabytes of data associated with that. Presently, using the Lake Ensembler program, we've done 4 models in ISIMIP 3, and that's produced around 300 gigabytes of data. And we have another 4 models underway. So there's a lot of data, and it's not been used as much as we would like, actually. So I would really say that even if you don't want to get involved in simulations, you might want to get involved in analyzing some of the data that's already there. And finally, if this interests you, there is a link here where you can go and look at some of the paper ideas that are underway now in the lake sector. And if you have a new idea, you could add that to that. And one other thing, you could contact any of us, and if you're interested in being a part of the lake sector itself, we could add you to the mailing list, and you could then be able to attend the lake sector meetings that we have about twice a year as well. So that's what I wanted to say. I'm sorry I went a little over, but I hope I gave you a good overview of the ISIMIP lake sector.
Great, thank you, Don. Thank you for giving us a oversight of ISIMIP. Do you mind just stop sharing?
Try to stop sharing now. Yeah. Sorry. Yep.
Yeah. Good. Awesome, great. So our next speaker is Dr. Anna Ayala. She's a postdoctoral researcher at Uppsala University in Sweden. She graduated from the University of Granada in Spain in 2011 with a bachelor's in civil engineering. And she went on to do her master's in water quality science and technology, also from the same university in 2015. And she did her PhD in modeling impact climate change related change on the thermal responses of lakes, which was jointly awarded by Uppsala University and the University of Geneva in 2023. And she's her research is focused on process-based modeling of physical and biogeochemical processes in lakes, with a special focus on climate change. And as I said, she's currently a postdoc researcher at Uppsala, working on modeling global POC burial in lakes and reservoirs. So without further ado, Anna, the floor is yours.
Thank you, Lipa. You see my screen? Oh, great. So good afternoon, everyone. Today, I will show some results from the ISIMIP lake sector involving local lakes, assessing the impact of climate change on lake surface heat fluxes. So lakes are considered as sentinels of climate change, and the primary observed physical consequence of climate change on lakes are warming surface water temperature. So the process of lake mixing and stratification, including how lakes respond to climate and to climate change, and primarily controlled by turbulent and radiative exchange of heat between the lake surface and the atmosphere. One-dimensional hydrodynamic lake model are frequently used to characterize hydrodynamics in lakes due to their computational efficiency and the realistic temperature profile that they produce. So lake model driven by climate output, how those provided by ISIMIP, allows to understand how lake water environment could behave and the different emission scenarios. So let's go to the lake heat budgets. So the heat budget of a lake is the exchange of heat with the surrounding environment, including the heat losses or gain most of which occur at the lake surface. Heat is also lost or gained to the lake below the surface from the inflow or also outflow, sediment heat exchange, and the attenuation of penetrative radiation within the water column. So surface heat fluxes include solar radiation, which vary depending of time of the day, season, latitude, water condition, and topography. And anthropogenic aerosol played a role affecting scattering and absorption of solar radiation. The albedo is controlled the portion of the incoming shower radiation reflected by the lake surface. We also have the incoming long-wave radiation, which is the thermal infrared flux from the atmosphere and depend mainly of the atmospheric temperature, moisture, cloud cover, and the concentration of the greenhouse gases. The increase in the greenhouse gases has led to an increase in the incoming long-wave radiation, which has resulted in a warmer air temperature. Long-wave radiation is also emitted from the lake surface, has a function of the 4 power of the surface water temperature, and his losses to the atmosphere by long-wave radiation are intensified due to the warmer lake surface water temperature. So also we have latent and sensible heat fluxes, also now has turbulent heat fluxes. And these are bidirectional fluxes. So the latent heat flux is the energy loss or gain due to evaporation and condensation, and depend on the vertical vapor pressure gradient and the air-water boundary. And the sensible heat flux is the draft of heat via turbulent processes between the lake surface and the atmosphere, and depend on the vertical temperature gradient at that boundary. So the turbulent heat fluxes also are controlled by wind and the static stability of the overlying air. Most of the latent heat flux occur as evaporation, and most of the sensible heat flux result in a heat loss from the lake. And the latent heat flux is often the main component of the turbulent heat fluxes. So the advective heat flux can have a warming or a cooling effect on lakes, water temperature depending on the seasonal difference between the inflow and lake surface water temperature. And this heat exchange with the sediment is generally transported from the water column into the sediment by conduction during the warm season and released back to the water during the cold season. So in this study, the advective and the geothermal heat fluxes were set to 0. So the heat content variation is computed by considering only the surface heat fluxes. So climate change is also affecting other essential climate variables such as wind and specific humidity. And all these changes have a direct impact on the individual surface heat fluxes component. So surface heat fluxes can be parameterized employing both formulas that require like surface water temperature and meteorological data. Here we use the 1D hydrodynamic line model system to parameterize the lake surface heat fluxes. So system was formed by ISIMIP to be data from 4 different climate models for the pre-industrial controlled scenario, which is an scenario without anthropogenic climate warming, the historical scenario based in historical changes in atmospheric CO2, and 3 emission scenarios that cover a range of potential future global radiative forcing from anthropogenic greenhouse gases. The study site is the Sofia. It is located in the west coast of Ireland, and Sofia is a monomictic oligotrophic humid lake with a surface area approximately of 4 kilometers square, a maximum depth of 46.8 meters, and a mean depth of 14.5 meters. So here, we can observe the projected annual volume weighted average lake temperature in blue for the PE control scenario, and in black for the historical scenario, and in yellow, orange, and red, the 3 future scenarios for low to high emissions. For the 3 future emission scenario, we can observe a significant increase with an average increase from 0.64 degrees under RCP 2.6 to 2.75 degrees Celsius under RCP 8.5 relative to the historical period. However, for the P control scenario, the lake water temperature decrease slightly around 0.12 degrees Celsius. If we now look at the total of net surface heat flux, so the annual mean on the left panel and the average over this 124-year period on the right, the total surface heat flux showed a very small positive imbalance with no significant trend for the 3 future emission scenarios. On the other hand, on the P control, heat output exceeded heat input, resulted in a very small negative heat loss. So here on the right are the radiative fluxes. So the net radiation is dominated by the net shower radiation, has incoming and ongoing long radiation and large, but opposite direction leading a relatively small net long radiation loss. On the left are the turbulent flat heat fluxes, so sensible and latent heat fluxes that produce a net surface heat loss. Most of the net radiation is balanced by the turbulent heat fluxes. So while a large change in the individual component of the heat fluxes occurs, it is a small imbalance between the turbulent and radiative fluxes that lead to a net heat gain or heat loss. So the turbulent and radiative surface heat fluxes show significant changes in the future emission scenario over time, primarily for latent heat fluxes, incoming long radiation, and ongoing long radiation. However, P control show no significant changes. The sensible heat flux was the lower contribution to the lake heat loss, with the greater heat loss projected for P control, while it was slower for the future emission scenario. And the net shower radiation contribute lower heat input and the future emission scenario than for P control. So here we can see the projected surface fluxes as seasonal scale. So the P control is in blue, and the RCP 8.5, which is the high emission scenario, is in red. So the total of the net surface heat flux is represented by the solid lines, the net radiative budget by the dashed line, and the turbulent heat flux by the dotted lines. And the volume weighted average temperature is represented by the lightest solid lines. So that's not here. So we can see that the largest changes in total surface heat fluxes were projected here in spring and in autumn, while small changes were projected in summer and in winter. In spring, so net heating was projected to significantly decrease as a result of an increase in lake heat loss by sensible and latent heat fluxes. In autumn, so net cooling was also projected to significantly decrease. And here, sensible latent heat fluxes are projected to change in opposite direction and in equal magnitude, with latent heat losses increasing and sensible heat losses decreasing, canceling each other out. So the turbulent heat fluxes did not change that much on the future scenarios, while net radiative fluxes was projected to increase on the future scenario, and all of these lead to a decrease in autumnal net cooling. So this result lead to a quantity result that in a warming world, there will be less heat no more entering the low sphere than in the springtime, and little changes in the net heating over the summer or winter compared to natural climate conditions. And the projected increase in lake water temperature is found to be largely because a reducing heat load during the autumn period. So summarizing, we can say that a significant increase in radiative fluxes formed by large changes in the individual radiative heat fluxes was largely contracted by significant decreases in turbulent heat fluxes, and the combined changes in the individual fluxes lead to a small positive imbalance in the long-term total surface heat fluxes, resulting in a significant increase in lake water temperature. And on a seasonal scale, the largest changes in net surface heat fluxes were in the spring and autumn, both spring heating and autumnal cooling significantly decreasing on the future emission scenario, while a small difference in net surface heat fluxes between P control and future emission scenario were projected in summer, in winter. I expanded this analysis over 47 lakes located mostly in North America and in Europe, and 5 of them in Oceania. And the lake covered a wide range of surface area, maximum depth, and also lake transparency, and include dimictic, monomictic, and polymictic lakes. Here, annual comparison between lakes with different periods of ice cover were impossible because the surface heat fluxes are not full parameterized under lake ice conditioning system. Then we focus on the summer period when the lake is strongly stratified and the surface layer is almost thermally isolated from the subsurface water. And the projected changes in summer surface water temperature will be controlled mainly by changes in the individual surface heat fluxes component. So before going through the findings, so to quantify the effect of climate change, I compared the projected surface heat fluxes for the historical period, which is this one here in black, with those associated with the late century climate change. So first, here we can observe the projected summer surface light temperature in black for the historical scenario, and in yellow, orange, and red, the 3 future scenarios from low to high emissions. Surface water temperature is projected to significantly increase for all the lakes for each future emission scenario. So we can see here, where each dot represents the absolute summer temperature difference for each lake, that the average increase range from 1.8 Celsius degree under the more optimistic scenario to 4.7 degrees Celsius under the worst case scenarios. So the increase in surface water temperature was the result of increased absorption of solar radiation and of long-wave radiation, with the largest increases projected for the incoming long-wave radiation. And as a result of higher surface water temperature, lake surface emit additional heat to the atmosphere by outgoing long-wave radiation and latent heat flux. Both in outgoing long-wave radiation and latent heat fluxes contribute equally on average to the increased emitted heat flux from the lake surface. In contrast, a decrease in sensible heat flux was projected because some surface water temperature was projected to increase less than air temperature. So this modification in heat output suggests a shift in the contribution of heat loss, fluxes, and the future climate conditions, with latent heat flux gain relative importance. So the projected changes in the individual surface heat fluxes component by the end of the 21st century occur in opposite direction, and they tend to cancel at each other, leading to an overall small change in the total heat budget over the summer, with the average total surface heat flux be almost the same almost the same under both historical and future conditions, similar to the result reported in Sofia during summer. However, when we examine each lake, total surface fluxes could experience a future increase or decrease relative to the historical condition. This is in part due to the restricted time period that I analyzed. So that analyzed time period was summer, which is June, July, and August in the northern hemisphere, and December, January, and February in the southern hemisphere. So the 47 lakes include in this study varied the latitude and morphometry, which means that they modulate the seasonal heat budget. So for example, for those lakes where the thermal certification is found in late spring and early summer during the historical period, these are ice-covered lakes at high latitude. The surface heat fluxes during the summer will correspond with this one inside this box, with a decrease in total surface heat fluxes at the beginning of the summer, resulting in a projected decrease in total surface heat fluxes at the end of the 21st century relative to the historical period. And for those lakes where maximum heat content at the surface is reached at the end of the summer during the historical period, these are deep monometric lakes, so the projected summer surface heat fluxes could be the one inside this box. With a decrease in the net cooling at the end of the summer, resulting in a projected increase in summer total surface heat flux at the end of the 21st century relative to the historical period. So summarizing, so we can say that the individual surface heat flux components were projected to change substantially under the future emission scenario. Achieving the contribution of the individual heat flux was projected with latent heat fluxes gain relative importance, and the combined changes in individual surface heat fluxes show that the accumulation of heat in the lake over the summer remained almost unchanged at the end of the 21st century. Yeah, this is it from my side. Thank you for your attention.
Thank you, Anna, for that insightful presentation. I should also mention that we will have time for questions at the end of the all four presenters' presentations. So next up, our next speaker is Sofia Fuente, and she holds a bachelor's degree in civil engineering from the Universidad Mayor de San Simon in Bolivia, and a master's degree in water resource engineering from KU Leuven University in Belgium. She worked for 3 years on sanitation, irrigation, and hydropower generation projects, and she is currently awaiting her PhD defense, and her research focuses on the impacts of climate change on lake evaporation at local, regional, and global scales using an ensemble approach. So without further ado, Sophie, the floor is yours.
Thank you so much, Lisa. I'm gonna share my screen. Can you see my screen? Oops, I think
We
I'm
see
sharing.
papers.
Yeah, sorry. I'm gonna try to share my screen. There you go. Can you see my screen now?
Yes.
Awesome. Thank you so much, Lisa. Okay, I'm gonna start now.
Sophie,
oh.
we see it in presenter note.
Odd. I'm trying to put the file here. Sorry, I'm gonna try to change this because I'm using two screens and it's just a little bit annoying. Give me a second, please. Maybe I have to do this. Yes. So can you see my screen now?
Yes, good.
Okay, good. So, hi everyone. My name is Sofia Fuente. My name is Sofia Fuente, and I'm going to present the last chapter of my PhD research titled Ensemble Modeling of Global Evaporation under Climate Change. So in this case, I use the global simulations from the ISIMIP round 2B. So as many of you already might know, lakes hold around 80% of the surface freshwater available on Earth and are essential for drinking water, agriculture, energy, transportation, and recreation. And therefore, lakes have been included in the United Nations Sustainable Development Goals. So because of their nature of open water areas, lakes can lose large amounts of water through evaporation. And this can have various impacts in the ecosystem functioning of lakes, with one of the most important being on lake water level fluctuations. As you can see on the photo there of Lake Mead, that had at the time lost a considerable amount of water, with an average of 6 foot, if I'm not mistaken, of water per year that are missing in that lake. So, however, evaporation is highly sensitive to the choice of model and method. And there are various studies that already highlighted this. But one way to work around this is to use an ensemble approach, which consists of combining multiple models and taking advantage of the diversity and the advantages of these models. And it also allows you for the uncertainty quantification. For instance, if you see at the figure on below there, you can have different individual model projections by different models, and the ensemble approach basically considers all the ranges and uses the average of this ensemble of combinations. And you can also, as already mentioned, quantify the uncertainty. So Don already explained this very nicely about the different models available and all the data that is from the ISIMIP 2B. And for this specific study, I used model simulations from the lake models ALBM, Simstrad, and Big Lake. And each of these lake models were driven by 4 general circulation models. I used both the simulations for the historic and the RCP scenarios. So I focused mostly on using latent heat flux and lake surface water temperature from these simulations. So I used the relationship that you can find in the Henderson-Sellers from 1986 paper to estimate evaporation rates for each of these lakes. And something very important to mention is that we focused on the warm season period. So we neglected all those times where the lakes were experiencing ice cover or were experiencing ice. So in addition to this, we estimated the uncertainty in future evaporation projections using an ANOVA method, and we focus on lake model and GCM uncertainty. So all the changes that were estimated in this study were calculated with respect to the reference period 1970 to 1999. So in this figure, you can see one of the most important results of the paper, which is the global evaporation change by the end of the century under the pessimistic scenario RCP 8.5. And if you look at the columns, you will find the different lake models. So ALBM is here, Simstrad and Big Lake, and the combination of the GCMs are in the rows. So GFDL ESM to M is on the top of the rows, and MIROC 5 is in the bottom. So one of the most important findings of this paper is that all models projected an increase in evaporation, which is consistent with previous studies. But what was very interesting about this is that if you look closely at the projections, for instance, of ALBM and the projections from Simstrat, you already see like notorious differences in the evaporation changes in the eastern region of the United States. And even if you look into the same lake model, but different GCMs, you already see like very important differences between GCMs over the same lake model. Like for instance here, in the case of ALBM, for this GCM, like the highest increases in evaporation were projected like in the central United States. So these regional differences made us conclude that the change was considerably. So the change in evaporation varied considerably across the model ensemble. When we quantify the global change across each lake model and GCM, we estimated that on average, lake evaporation increased along for ALBM across the different GCMs. It varied between 23% and 52%. So almost twice the difference between one and the other. In the case of Simstrat, when we also estimated for each of the GCMs the global average evaporation, we also calculated a variation in the changes between 13 and 29%. And in the case of the last model, Big Lake, the changes in evaporation varied between 16 and 33%. So and because we have all these considerable differences in evaporation changes across the model ensemble, we use all model realizations to estimate, to project the results. So the global average evaporation when using all model realizations was projected to increase by 27% by the end of this century. So regarding the uncertainty analysis, here you will see the figure of the uncertainty contribution in future evaporation changes for the RCP 8.5 scenario. So on the top of the figure, you will find the GCM uncertainty, and on the bottom, you will find the lake model uncertainty. What we found from our results is that on average, GCM accounted for 74% of the variance in future lake evaporation. But we also noticed that there were these uncertainty sources varied among regions. For instance, you can see in this figure, in this map, that most of the lakes have like an uncertainty of between 80 and 100% for GCM. But if you look at the bottom panel in lake model uncertainty, you will see that like the northernmost lakes in this region, parts of South America, Africa, and Tibetan Plateau had like a larger uncertainty due to lake model. So this made us conclude that not only the choice of lake model is important in simulating lake evaporation, but also the choice of GCM was important. So the take-home message of this presentation is that using a single model realization to simulate a global lake evaporation might be problematic because of the differences that I explained before. It was also important to highlight that GCM had a greater contribution than lake model to evaporation variance. And finally, the global annual lake evaporation rates that we projected in this study are higher than the 16% earlier predicted by what the Wang et al. In 2018 paper. So if you're interested on learning more about this research, it had recently been accepted for publication in the Journal of Hydrology, and it will probably become available online in the coming weeks. And if you have any questions, you can always shoot me an email or on Twitter. Thank you so much.
Thank you, Sophie, for such a thought-provoking presentation, and good luck with your defense next week.
Thank you.
So our final presenter is Dr. Daniel Mercado, and His research focuses on the analysis and processing of climate, hydrological, limnological, and water quality data to make forecasts and aid decision making. He has experience in climate change simulations at global, regional, and local scales, in data processing, data analysis, and using high-performance computing clusters. So, Daniel, over to you.
Hi, Lipa. Hi, everyone. Thank you. I'm happy to be here. I will try to be fast so we have time for questions. Can you see my slides in full mode? Yeah. Okay.
Yes.
So I'm just now going to talk about two ways that you can use ISIMIP data. So the first way is that you can download data for climate change scenarios, so meteorological data that then you can use for your case study. For instance, as Don said already, you can use it for lake modeling. So you will find the usual meteorological variable that you need, and then you can apply it and obtain output for your lakes, particular case studies. Then the second option and the second way to use ISIMIP data is just to directly use the output from the impact models. So you already know that we have different sectors. We have the water sector, the hydrology, biomes, we have forests, we have agriculture, and we have many others. So we have also the lake sector. So we have output also from the lake sector after forcing all the lakes, the lake models. And then we obtain water temperature, ice certification, and many other variables that I will show you now, that you can see the full list of them in the protocol of ISIMIP. Then ISIMIP, let's say, it has two big branches. One of the branches is ISIMIP 3A. So we have also ISIMIP 3B. So ISIMIP 3A is based on reanalysis. If you don't know what is a reanalysis, you can go to this link here. I will share also this presentation and have a look at it. But in summary, a reanalysis is just also a model, but it's based on real observation. I mean, in situ measurements, is based on remote sensing, is based on even buoys in the ocean. So they take many sources of data, and then they produce historical, real observation. They are called pseudo observation. So at the end, you have a historical period, is from 1901 until the present day. So we have four main models for ISIMIP, and let's have a look immediately to the protocol just to see how it looks and how can we access to it. So we just go to protocol.isimip.org, and then you will find this web page where you will find all the details about ISIMIP, about how to download the data, how to contribute if you want to simulate and obtain your own results, and then upload your results to the ISIMIP archive. So, but now let's focus on this ISIMIP 3A. So here you can select ISIMIP 3B or ISIMIP 3A. Here you see that you have all the sectors that are at the moment an ISIMIP. Now let's go to the input data, and here you will see that you have the four main models that I was talking before. This last one, Chelsea, is one that was added in the last weeks. So, but the first four are the main ones. So if you want to know the details, you just click on the model, and then you will find the source of these models. For instance, this is a combination of two other reanalyses. You will find all the variables that are contained in this reanalysis, also the time span, and so on. So if you click here in the help, you will find the names of each of these variables. So for instance, this one is relative humidity, and so on. So let's go back for a minute again to the presentation. Then let's go to ISIMIP 3B. ISIMIP 3B is the climate scenario that we know, like for instance, historical, PI control, and all the future scenarios is the regular, the ones we are used to hear about. And for this one, we have 5 models. I mean, Don already talked about them, but I just want to be clear and let you know that there are many groups developing simulations. I mean, it's not only ISIMIP only gathered 5 models, but as you can see here in this map, and this is the source of the map in the bottom. In this map, we have 49 different climate models that are simulated for CIMIP 6, which is the new phase of the climate models. So if you go to this webpage, ESGF, you will find all the models. So there are hundreds of models because every group has a different running for each model, depending on the initial conditions, on the boundary conditions, and so on. So the good thing with ISIMIP is that they just selected 5 models for us. So it's easy for us to just access the data, so we don't have to have a look at hundreds of different models and simulation, but only 5, okay? So then we have these 5 models, and we have, of course, the 5 scenarios, historical, PI control, and the 3 for the future. And at the end, we have 25 different simulations. And you can also, again, see all the details here in protocol.isimip.org. Then what does the scenario, how does the scenarios work? So for the historical period is like historical changes of CO2 and methane concentration. So let's say the current circumstances. Then you have PI control, which is removing this CO2 concentration and fixing the concentration at the level of 1850. And then you have the future scenarios. And for the future scenario, there are many other, not many, but a few more scenarios, and it's just a combination of these shared socioeconomic pathways and representative concentration. So this is just related, the first one related to policy, and the second one related to greenhouse gas emission. So in ISIMIP, that's another good thing of ISIMIP, they already selected for us 3 scenarios that we can directly use, and they will represent, like, let's say, the whole range of uncertainty when we are talking about climate change. So we have a worst case scenario, we have the best case scenario, and we have one in the middle. Okay, so now that you have, let's say, more or less the basis, I mean, if you have questions, please let us know, and you can also write us an email afterwards. But what we do then in the lake sector is just taking all these databases, all these huge climate databases, we implement lake models. You can see here all the models that which maybe you have used them already. So this is the list. And for instance, if you are running a different model and you want to be part of ISIMIP, by producing new outputs, you can also write us, and you can also be part of ISIMIP in that way, not only using data, but also producing outputs. And then at the end, we produce lake outputs, and then we upload all these outputs to ISIMIP. Then at the end, we have a huge archive with all the information that you can access using data, this link, which is data.isimip.org. Let me just close this. So you come here, and then you will find all the data. So we will find the climate forcing that you can directly use for your case study, or you can also go to the output data for the different sectors and also download the data from them and use them for whatever thing you want to use them. So let's just click and have a look how it looks. So this is the repository of all the data. So here in the left side, if you follow my cursor, you will see that we have ISIMIP 2A, ISIMIP 2B. This is the previous phase of ISIMIP. So this is using CIMIP 5 models, so the previous phase of climate models. And ISIMIP 3A and 3B is using the new CIMIP 6 climate model. So we encourage people to use the new models because they have new socioeconomic pathways, the new socioeconomic pathways added already in the future scenarios. And so if you click on this, then you go, for instance, we go for ISIMIP 3, which is the climate change scenario. We click on input data, just in case you need climate forcing. You click on climate forcing, then atmospheric forcing. I mean, feel free to just have a look at it, and you have also here the metadata, the documentation, and all the information you can need. And then you go to, let's go to GFDL, let's click on historical, for instance. Let's click, for instance, in case you need precipitation. Then you will see here the database for precipitation. So here, this long name is very easy, it's nothing complicated. This is first the climate model. These are the different initial and boundary condition of the model, but you don't have to care about it. I mean, this is the W5EC, is the bias correction applied to this model. This is historical, which is the historical scenario. PR means precipitation, and then you have a global database, and then you have the daily temporal resolution. So be careful, don't click here on download all file because it will start downloading everything and it's many gigabytes. So I recommend you to first click here on configure download. Okay, so if you, for instance, well, at least, I mean, if you need to download the whole file, I mean, if you click on the file, you go here, you will see all the different netcdf file that you will have at the end if you click on download all. Okay, so it will be each one of them 2 GB. This is in case you need to implement a global simulation, for instance. But if you want to only download data for one specific point in the world, for instance, one specific lake or river or whatever, you just let me, because this one doesn't allow me. Okay, I don't know why it doesn't allow me to see the, sorry, here. Okay, so here, this is the other option. So you click on, remember, you click on configure download, and then after clicking on configure download, you then select, for instance, the time range you need. If you need, for instance, the last, this is historical, remember, but you will have, if you click on future, you will have until 2100. So for instance, let's say that you need the last 4 years. And then, for instance, if you want to cut in a specific area, you can also select the point here, I mean, the latitude and longitude. And here below, this is important, below are the commands that internally the database is applying to cut the netcdf, the huge netcdf for only the data you need, okay? So if in case you want to redo it by yourself, so this is NCO, and this, for instance, here is CDO. These are just climate tools used to work with netcdf, but you don't have to worry about it. So feel free to have a look at it and just click and try it. You can also select by countries, but let's select by point, for instance, and then you click on, let's say, 45 degrees and let's say 3 longitude, which is more or less in Spain. And then you click on download, and then you will be in queue. Hopefully it will be fast. Otherwise, I will just, let me stop sharing first. I will share my whole screen, sorry, but just to show you everything. I mean, just to let you know that I'm telling you the truth. So once you finish the download, you will see here that you have a time series. It's an Excel file with the date and the values of, in this case, precipitation, for instance. Then in the same way, actually it finished the download. So here is a zip file. You can see it here. It's a zip file, and again, it's a text file, a CSV that you can already use for your case study. Then another option is just to directly, not downloading climate data, but directly downloading output data from the lake sector. So you go, at the moment, we don't have lake global. I mean, we don't have data for the whole world yet. I mean, we have it already, but it's still under quality control, and probably you will have it. We will have it in 2 or 3 months available for everyone. And if you need it right now, please contact us, and we can also provide this data by other means. Okay. So then you can click on lakes. You have different versions, for instance, for the Flake, GLM, Gotham, and Cistern. This was done by Jorrit and Johannes in the last days. Then you have again the models, and then you have the scenarios, and then you have the different variables for the lake in this case. Then you can click on them, and then you can access to this data. For instance, these are local lake, these are calibrated lakes. So this is, for instance, Lake Alequah, Chalkeva, Ani, and so on. So we have in total 73. If your lake is not here, you can then use global simulation and select, for instance, the closest pixels to your lake, like to have a first view of what is climate change, how is climate change impacting your lake. But then you can also download climate data and use it in your lake modeling as well. Yeah, I think that's it. Thank you, Lipa.
Great, thank you, Daniel, for that presentation. I think we have time for questions. If people have any questions to ask the the presenters, they can go ahead and unmute themselves and just ask the question. Jort?
Hey, thank you all for your presentation. I had a question maybe for Danielle, but anyone can answer. I had a look a bit at the ISIMIP download portal. Can you also download the meteorological forcing for the local lakes from there, or not?
No, no. It's not here for now, I think. Did you access to the data using DKRZ, right? The database?
Yes,
Oh.
so I got it through the
Yeah, it's not the,
simulations.
no,
Okay.
not for the local lake. That's a good, sorry, that's a good point that we should also communicate to the ISIMIP team to see if they can also provide this. Yeah, but you are right. It's not there yet. No.
Matap, you can go ahead.
Hello everyone. Thank you for all your presentation. I have a question probably from oh, sorry. I forgot the name. About the evaporation study. Sofia, yeah, sorry. Sorry. I have a question. How did you, maybe it's a very hard question, but in a conceptual way, I just want to know how did you separate the uncertainty of the model, of GCM models and the lake models? Is that not a very easy question? You can
Oh, yes,
just...
I can attempt to answer it. So yeah, I guess you're coming from the, and thank you for your question, Mata. So I guess you mean because all these the GCM and the lake models are tangled. So each of these realizations are already including the GCM and the lake model uncertainty with each other, right? So what I did is to use an analysis of variance. And there I considered all the sources of uncertainty. You can always include more sources if you have the data. In this case, for instance, you could use parameter uncertainty, you could use scenario uncertainty, but in this case, the focus was to see which one of the two were more important. So I just used those two. Yeah, basically just an ANOVA analysis on each of the lakes and run on the simulation. And that was pretty much it.
And thank you for your answer. But for the climate models, did you actually check with the observational temp or evaporation? I don't know if it's recorded or not, to see that if which models actually can simulate the evaporation better or not. Did you do something like this to calculate the mismatching errors between the observational and the model in the, I don't know, historical period in whatever ages you have?
Yeah, that's a good question. So I should have probably pointed out that these global simulations are based on what we call, or what the ISIMIP calls, the representative lakes. So they are not like real lakes to make a comparison with observations. So it's like you have a grid, imagine just a grid of 0.5 degrees, and all the lakes that were falling within that grid where you were making an average of the lakes that were falling into that grid and taking the average depth and area. And then this grid is kind of representing those lakes. So making a comparison with observations wouldn't make much sense in this case. But the good news about the global simulations is that the lake models that were used by the ISIMIP have been widely validated in a number of studies. So we already know that these lake models are robust and do a good job simulating lake evaporation. I actually tested this with the local simulations for Lake Kinneret, and I was able to verify that they do a great job in simulating lake evaporation.
Perfect. Thank you so much, Sofia.
Great. Can't see. Someone has their hand raised up, and I can't see who it is. Just go ahead and Curtis, go ahead and
Yes.
ask your question.
Yeah, thank you. Yeah, great presentations. I was curious, so the global model is a half-degree grid, which is rather coarse. So I'm wondering, when you're downloading the data, when you pick that latitude and longitude point, is that interpolating from that coarser grid to that point, or is it just grabbing the data from the nearest grid cell?
Is interpolating this.
Okay, nice.
Interpolating this. Yeah, and also remember that you could also, I mean, if you think it's too coarse, the resolution for your case study, you could also download the climate data and run your own model, which will be also useful. I mean, in case you want more details on your lakes.
Mm-hmm. Thanks.
Any more questions? If you can't think of any question to ask now, you can always reach out to the presenters. I think that's it for today. I'd like to thank the presenters for giving this thought-provoking presentation on ISIMIP. And yeah, thank you for taking your time to give us this presentations. And to you, the participants, I'd encourage you to keep an eye out for future emails from the GSA workshop committee for future Limnoseries workshops. And also stay tuned to the Slack channel, because we also announce workshops there as well. So yeah, with that, I'd like to thank the presenters and everyone for participating.
Thank you so much, Lipa, for hosting this workshop.
Yeah.
Thank you, everyone. Thank you, Lipa.
Thank you,
Thank
everyone.
you.
Thank you.
Bye-bye.
Bye.